Okay, arithmetic sequences. So this is probably a formula that you've seen quite often. It has really to do with just a linear function, because if you think about it, arithmetic sequence is just a common difference between two numbers, be it addition or subtraction. And then a series is when we take that sequence of numbers and we start adding them together. So we'll talk about that towards the end. So just to make sure we understand these terms again, this a sub n is our nth term of our sequence. A sub 1, therefore, is our first term in our sequence. N is the term that we're working with. So for instance, if I said right here in the nth term, if we said a sub 5, then n in this case would be the fifth number in the sequence we're working with, so put a 5 right there. And then d is our common difference. I know you guys have worked with this a lot in the past, but just want to make sure that we review those variables and what they stand for, represent. So on example 1, I gave you this sequence of numbers. You can see it's pretty simple. There's just a common difference of 3. We're adding 3 between each term. Therefore, our common difference in this particular example is 3. So we'll say d equals 3. Okay, our next one, common difference. Well, it looks like we're decreasing this time. In fact, we're decreasing 4 each time. So we're going down 4. So our common difference is -4. And I'll let you do part C on your own and check it with the notes key on Canvas. Okay, our example 2, it's asking in an arithmetic sequence to find the nth term, given that our common difference is 5, and the first term in our sequence of numbers is -1. So you can see I labeled these with the variables given in the formula that we typically work with, which I'm going to rewrite it right here. So it's just a matter of substituting the values that were given in the correct position. So our first term is -1, so put it right there for a sub 1. Plus, well, we're looking for the nth term. Therefore, this is going to represent our nth term, leaving n in the equation. So we're going to leave n alone, just leave it at that variable, n-1, and then our common difference we were given is 5, and I'll go ahead and just bring this down for right now. So you could leave it like that, technically speaking, but you know, a lot of times they like to combine like terms and simplify, so I'll just go ahead and do that right here. So -1 plus 5n minus 5 after you distribute the 5 into the parentheses. So our nth term in this case is 5n minus 6. So this formula would represent the nth term of our sequence. So if we wanted to find the sequence of numbers, you could substitute, or any number rather, any position in that sequence, you could substitute that number in place of n and find what that number is in that particular sequence of numbers. Example 3 is saying what's the 10th term in our sequence that begin with 8 and 20. So we're looking for the 10th term. So when we use our formula that we usually work with, the a sub n equals a sub 1 plus n minus 1 times d, this time we're going to put a 10 in place of that n because we're looking for the 10th term. Now the first term in our sequence is 8 that was given to us. Well, we know n this time. N is the 10th number we're looking for, so that's going to go in place of n, so 10 minus 1. And then our common difference, well, between 8 and 20 here, we're adding 12, so it's going to be positive 12, so a common difference is 12 right there. It's just a matter of doing some arithmetic. Well, 12 times 9 is 108, so it looks like the 10th term in our sequence is 116. All right, here's another example. This time I gave you the 8th term in the sequence and the 12th term in the sequence of the arithmetic sequence, and we want to find the first 5 terms. Okay, so first thing we need to notice is if this is the 8th and the 12th, and that seems basic, that there are 4 terms in the gap, in the space between these, that we have not accounted for. So if we knew what the common difference was, that would be very helpful to us. So you can think about it, if we had 25 as our number we're working with, our 8th term, and we're trying to get all the way up to the 12th term, that means we're going to add the common difference 4 times. Or you can just say whatever the common difference is, which we don't know, but we can see whatever it is, you multiply it by 4 and add it to 25, then you should get our 12th term, which is 41. So now we can just solve this algebraic equation and determine that our 4th term is 4. Well, now we know our common difference rather is 4. So if you were to add 4 times, you would get to 41. Now, if we're looking for the first 5 terms in our sequence, you can pick either one of these. Let's just say I picked the 25. Went back to our normal formula. So we know that a sub n, if it was 25, we don't know the first term in our sequence. We're looking for that. If we knew it, that'd be nice. But we do know that 25 is the 8th term in the sequence. So 8 minus 1, we're going to substitute it in place of our formula. And we just found our common difference of 4, right? So that can go in that spot. So now we can solve this equation to figure out what our first term in our sequence is. So 25, a sub 1, well, 8 minus 1 is 7. 7 times 4 is 28. So it looks like our first term in our sequence is -3. So the instructions were to write the first 5 terms. So I'll just write down here, -3 is certainly our first term. We just found that. Remember, our common difference was 4. So if we just add 4 every single time, we can get our next 4 terms. So add 4, that would give us 1, 5, 9, and 13 would be our first 5 terms of this particular sequence. Okay, the last section we're going to deal with is the sum of finite arithmetic sequences. So finite just means countable. Essentially, the sequence stops. It's not infinite. So there's an exact number numbers that we can work with within our series. So like I said earlier, our sequences numbers, might look like this, but notice now we have pluses in between them. So that's when we start dealing with a series. We're actually going to be adding these up. So the formula for a finite sum of an arithmetic is, you can see in your notes, is given right here, where a sub 1 is still our first term in our sequence, or series rather, and then a sub n is our last term in the series, and then n just represents the number of terms in our series. Okay, so the number of terms that we have in our series. All right, so our very first one here, and deriving this formula is interesting. If you're curious as to how this formula is derived, just let me know. You can pop in on a tutorial session. I can show you. If I get enough responses, I guess if you really want to see it, I can show you how this is derived. But just to keep our notes a little bit more concise, I'm just going to use it today. So if we're trying to find, well, let me jump ahead of myself here. This one's not too bad. You can count how many of numbers there are in the sequence. But let me show you an example as though if you couldn't just simply say, well, the difference is 3 and just keep counting down to get to 22. How would you do it then? To figure out, because what we need to figure out first of all is how many numbers are in the sequence that we could put in our formula. So if we weren't sure, we'll just go back to what we've always done. Remember, this is scratched out. 22, we want to know what number in the sequence, what is this, our series, does 22 represent? So we're just going to treat it like an arithmetic sequence. We know our 22 is our last term. We know 40 is our first term. We want to know how many numbers there are in that sequence. We know our common difference is -3. So just like we did this earlier, just a matter of solving this equation. So distribute our -3. All right, so that's what, 43 right there. So -3n plus 43. I like to do this. I'm going to add 3n over and subtract the 22. So it looks like 22 is the 7th number if it were a sequence of terms being added together, which essentially means there are 7 numbers in this sequence. So now, our series. So now we can say, well, let's find what all those numbers add together would be. So we know 7 over 2, remember, because that's the number of terms in our sequence. And we're going to take our first term in the sequence, 40, and add it to the last term in our sequence, 22. So we have 7 over 2 is equal to 62. I would actually just take this 2 and 62 and divide them. So 7 and 31. So it looks like all of our numbers in this particular series are going to add to be 217. All right, next one. This one's a little easier to see. You can flat tell that there are 35 numbers here. And the difference we're working with right here is 1. We're adding 1 each time. So we're trying to find the sum of all those. I'll just work it off here to the side. So 35 over 2. Our first term is 1. And a sub n, our nth term, is 35, the last term in our series. So it looks like we're going to have 35 over 2 is equal to times 36. All right, so we're looking at 35 times 18, which is 630, I believe. Part C, what's the 50th partial sum of this particular series of numbers? So we have a sub 1. We need to figure out what's the last number in our sequence. So going back to this again, we need to figure out what is a sub 50. What is our 50th term? We know our first term is -6. We know 50 minus 1. And we know our common difference right here is that it's adding 4 every single time. So we can put that right there as our equation. And just to kind of save a little bit of space here, if you do all that, which by the way, I'm okay with using a calculator, that'd be 190. And now we know that our first and last term, it's just 50 over 2. Our first term in our sequence is -6. And we just found the 50th term, the last term in our series, is 190. It's just a matter of plugging all that in. You can use a calculator again, which is 4,600. So that would be our 50th partial sum. All right, final problem of our notes, as we have this series right here given in sigma notation. So first thing I would like to do, if I was given this problem, is to list out our series and actually see what those numbers look like. So if we were to plug 1 in place of I, right? So 4 times 1 minus 1, well, you would get 3. All right, if you were to do the same thing, plug the next number in, 2, for instance, you would get 7. I'll do it one more time. 4 times 3 minus 1, right? Because we just add 1 each time. Started at the first term. We're going to keep on continue going until it gets to 25th, but essentially, what's that? 12 minus 1 is 11. So this is basically equal to 3 plus 7 plus 11 plus, we could continue to keep going until we got to the very last one, which we know is 25, right? So dot, 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 I'll just say 4 times 25 minus 1, right, which is what, 99? So this would be our series right here that we're looking at, right? So this is probably a better visual of what we're having right here. 3 plus 7 plus 11, so on and so forth. So if we're trying to find the sum of that, all right, so we know there's 25 terms, and we're going to take our formula. Our first term is 3, and our last term is 99. Once again, if you want to use a calculator, I'm fine with that. But basically, we'll say that the 25th term, or sum of those 25 numbers in our series, comes out to be 1,275. All right, as always, if you have questions, please don't hesitate to ask. You guys stay out of the trees.